All right, so now we're looking at accelerated motion. We have a velocity versus time graph, and it's a little bit hard to see, but this object has no velocity, zero velocity for 2 seconds. So I'm going to add some numbers here. 1, 2, 3, 4, 6. Okay, then these are going up by 5, 10, 15, 20. So it's 0 meters per second for 2 seconds. And then its speed increases to 30 meters per second in 6 seconds, by 6 seconds. So it does it over 4 seconds. So describing Word's motion from 0 to 6 seconds. So starts at rest and then begins moving forward with increasing speed. It's moving forward, that's because it's a positive slope, and it's going, the velocity is going up, so the speed is going up. Determine the velocity the following times: 0 seconds and 3 seconds. So these you were just reading right, are 1 second and 3 seconds. You just read it right off the graph. So at 1 second, let's go up and see what we hit on the velocity. Oh, we don't have to go very far. It's 0 meters per second. So 0 meters per second. And then at 3 seconds, let's go up until we hit the line. Bam. And then we'll go over and see about where that's at. And people said different things. Some people said 7, 7.5. Some said 8. I tend to say 8. You know, we're just reading it off the graph. So 3 seconds to 8 meters per second. Okay, determine the acceleration of the object from 0 to 2 seconds and 2 to 6 seconds. So here's the key. Acceleration is the slope of v versus t. All right, so the slope is the rise, delta v, over the run, which we usually say is delta t. So A equals delta V over delta T. Now, usually we don't put the delta on the T there, just say T, but we can do that here. So, acceleration from 0 to 2. So A, delta V over, I'm going to put the delta on there for now. So from 0 to 2 seconds, our change in velocity is, well, it stays 0, so it's 0 meters per second divided by 2 seconds, which is 0 meters per second squared. And that's from 0 to 2. All right? From 2 to 4 seconds, A equals delta V over delta T. Now, there were some people in class who did the delta. Deltas are always, you know, you could write this as V final minus V initial over T final minus T initial. Deltas are always final minus initial, right? So delta V over delta T, well, I always just like to think, okay, if it's starting at 0, then our delta is simply whatever you've gained. So, oops, I probably should have drawn this arrow up a little higher, huh? So delta V, we were going up 30. So your deltas should be positive and negative depending on your graph, right? So it's plus 30 meters per second. And it doesn't start doing that to 2 seconds. So starting at 2 seconds up to 6 seconds to change that velocity, that's a time interval of 4 seconds. So 30 over 4 is 7.5 meters per second each second. I just leave the units that, okay? I'm not going to try putting the squared in. It's meters per second each second. So each second this thing's moving during this part of the time is gaining 7.5 meters per second. Determine the displacement of the object over this time interval. Area under the curve, all right? So area under the curve, well, there's no area under the curve for the first 2 seconds because it's not moving. Then it starts moving quickly, so our area under the curve becomes a triangle. It's literally the area of that shape. area under V versus T is displacement. Okay? So to find the area under a triangle, right, I'm going to redraw it here. We have a base on that triangle of 4 seconds. The height of that triangle is 30 meters per second. Right? So delta x is the area, 1/2 base times height, because it's a triangle, so 1/2 of 4 seconds times 30 meters per second. So it's 4 times 30, 120. The seconds cancel. Half of 120 is 60 meters. Okay? Area under their curve. All right, sketch the graphs for position versus time and acceleration versus time. I'm going to start with the acceleration versus time. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5 on the position. So 1, 2, 3, 4, 5, 6. We go from 0 acceleration up to 8 meters per second. So I'll go 2, 4, 6, 8, 10, 12. 2, 4, 12. And the units are meters per second squared and seconds. Or meters per second, I guess I should say. So we started off with no acceleration for the first 2 seconds. And then it goes up to 8 meters per second squared for the last 4 seconds. You can make the line down if you want as well. So now, we got to do our position versus time graph, right? So it moved 60 meters, so we got to get out to 60 meters. So let's see here. 10, 20, 30, 40, 50, 60, and the units are meters. All right, but for the first 2 seconds, it's not moving. Then its position, this is going to be a curved line because our we have acceleration. So it ends at 60 meters. All right, so I'm going to put that at 6 seconds. 60 meters at 6 seconds. And it gets up there with a curve. So I just kind of draw a curved line. Don't get too fancy. You could plot more points if you wanted to. You could solve for 5 and, you know, you can go there. But that's good enough. All right, let's look at problem 2. That'll be it for this video here, I think. Actually, we'll go on to the next one a little tiny bit. So let's look at problem 2. The graph below represents the motion of an object. So this is an object that is traveling along a straight line. At what point on the graph above is the object moving most slowly? So remember, v equals the slope of the line. But this is a curve, right? Well, it's the tangent line in that case. Use your slopeometer, right? So wherever the slope is steep, it's moving fast. Wherever the slope is positive, it's moving forward. Wherever the slope is negative, it's moving backwards. Wherever the slope is shallow, it's moving slowly. Because remember, the slope of this line, tangent to the curve, is the velocity. So it's moving slowly from beginning from 0 to A. But then at point, okay, moving slowly at what points? So B and F, slope of the line is 0. So therefore it's moving the very slowest. Over what intervals on the graph is the object speeding up? So intervals, speeding up is where the slope is getting steeper. So this is from beginning to A, because the slope's getting steeper. And then it's speeding up from B to C. All right. It's constant speed, and then it slows down, it speeds up also from F to G. This is the slope is getting steeper. Over what intervals on the graph above is the object slowing down? Well, this is where the slope's got to get more shallow. So It got up to a high speed at A, and then it's slowing down to B. So A to B, it's slowing down. And where else does it slow down? E to F. All right, and there's one more spot, right? G to the N, the slope is steep, and then the slope is getting shallower. Lower. Well, what points in the graph is it changing direction? Well, at B and F. The slope is changing from positive to negative at B and negative to positive at F. Right? There's a positive slope right before B, then it stops. Now it goes negative. It's heading backwards. It gets here, it slows down and stops, and then it starts going forward again, and then it slows down and stops. All right, so that's that. One last thing I want to look at here before this bell rings and I have to go to lunch duty, and that is pause here and recap the equations and definitions we've been using. So A equals delta V over T, all right, or A equals slope of V versus T graph. Delta X is slope, or sorry, not slope, it's area under V versus T. V is slope of X versus T. Yeah, and we got V equals delta X over T. Technically, this is average velocity now. We really need to make sure we call it this because we have accelerations going on here. It's average velocity equals displacement over time, so we'll be good to go there. And we'll pick this up later. Good timing.